Hello students, let us discuss valence bond theory in coordination compound. According to this theory, the metal atom or ion under the influence of ligands, it use N-1d, Ns, Np or Ns orbital of a central metal ion which undergoes hybridization. As the orbitals of central metal ion undergoes hybridization, it results in an equivalent orbitals of definite geometry. Because of this, it gives definite geometry. So that is the hybridization which we are going to discuss in the valence bond theory. So the definite geometry which is formed, these are tetrahedral when the coordination number is 4. Hybridization, it undergoes, if it is sp3 hybridization, the geometry is tetrahedral where M is the central metal ion and the ligands are at the 4 centers of a tetrahedral geometry. And if the coordination number is 4 and if the hybridization is dsp2, that the geometry is square planar where the M is the central metal ion and the ligands are taking the position of 4 corners of a regular square planar geometry. If the coordination number is 5, then the hybridization sp3d, then the geometry is trigonal bipyramidal where the M is the central metal ion and the ligands are taking the 5 position here, that is 3 are taking the equatorial position and the 2 ligands are taking the axial position. This geometry is called as trigonal bipyramidal. And if the coordination number is 6, then the 2 possibilities are there. It can either form inner D complex or outer D complex. That is, in sp3d2, Nd orbitals are involved in hybridization, but in d2sp3, the inner d orbitals, that is n-1d orbitals are getting hybridized. So that is the difference here. sp3d2, that is the outer d orbitals are involved, that is Nd orbitals are involved. Here the orbitals that is involved is the inner d orbital, that is n-1d orbitals are involving in the hybridization. But the geometry formed is same for both, that is octahedral geometry. Octahedral geometry where M is the central metal ion and the ligands are taking the position like this. So this is what the geometry and the hybridization. This table, once you learn it, it will be very easy to predict the geometry and the hybridization depending upon the coordination number. As when the coordination number is 4, the 2 possibilities are there, that is sp3 or dsp2. If the coordination number 6 are there, then 2 possibilities are there, that is sp3d2 or d2sp3. But if the coordination number 5, then there is one possibility, that is sp3d. So how we can find it out which type of hybridization is there in a particular complex, that we need to discuss here. So let us take some examples. These examples are given in the textbook also. So we'll be going to discuss that examples. Let us take first example here, that is CONH363 positive. So we are going to doing the hybridization for this complex. First of all, here the orbitals of central metal ion is undergoing hybridization. So first of all, identify the central metal ion, that is CO3 plus is the central metal ion. Remember here the charge of that ion is important here, because when you find out the oxidation state of cobalt here, that is CO, it having 3 positive, that is CO3 positive ion. So write down the electronic configuration phase CO3 plus. CO having the atomic number 27. So its ground state configuration is 3d7 4s2. But CO3 positive means you have to remove 3 electron, that is 2 electron from 4s and 1 electron from D is to be removed. So how much is remaining? 6. That means 3d6 is the configuration for CO3 plus. So that we have to write here. So that is written here. We have made 3d orbital, then 4s, 4p. 4s and 4p are empty orbitals here. So 3d orbital having 6 electron, that you can count 1, 2, 3, 4, 5, and this is the 6th electron. So you have to make the 6 electrons, that is represented here in the form of arrow mark. Now here in the case of the ligands are actually placing a very important role here. Depending upon the ligand, here either the pairing is taking place. So here the ligand ammonia NH3 is a strong field ligand, according to ligand field theory. So it will causes the pairing of electron. Pairing of electron means the electron which is in the D, it gets start to pair up. So when it gets start to pair up, that means in order to make the bond with 6 ammonia, 6 vacant spaces are required. Why it is 6? In the formula you can see 6 ammonias are there. So 6 vacant spaces are required here. So the strong field ligand will causes the pairing of electron. So the possibility here, coordination number is 6. So what are the two possible hybridization that we have discussed? It can be either sp3d2 or d2sp3. So we have to identify which type of hybridization. When there is a strong field, so then the possibility is inner D orbitals are more possibility in the hybridization. So the possibility is d2sp3. So let us check with that example. So in this example, ammonia is a strong field. So the pairing begins. And when the pairing begins here, the electron in the D, as here 6 electrons are there, these electrons start to get pairing. That means 1 electron from here get paired this side. That is 1 electron, 1 unpaired electron will get pair here, and 1 electron from here it will get pair. So the 6 electron will get paired like this. So here 2 orbitals which is vacant now, and the s orbital and the p orbitals, here 3 p orbitals are vacant. So these will get hybridized. That means it undergoes the intermixing of these orbitals. Whichever orbitals are involved here, the 2 orbitals of d, that is n-1 d orbital, 1 s orbital, that is 2 d orbital, 1 s orbital, and 3 p orbital. These 3 p orbitals, it get hybridized. So what is the type of hybridization? That is d2sp3 hybridization. So this is actually nothing but shown here. That is the 2 orbitals of d, 1 orbital of s, and 3 p orbitals undergoes hybridization. Therefore it is called as d2sp3. Now why we are writing d2 here? Because inner d are involved. This is n-1 d orbital, this is ns orbital, and this is np orbital. So n-1 d means which d? Inner d orbital is involving in the hybridization. Therefore the hybridization is d2sp3. And because here the hybridization in which the inner d orbitals are involved, so this type of hybridization, it results in the formation of a complex that is called as inner orbital complex. It is called as inner orbital complex, or it is also called as low spin complex. This is very important. Why it is called as inner orbital complexes? Because inner d orbitals are involved in the hybridization, and it also called as low spin complex, or it is also called as spin paired complex, or it is also called as spin paired complex. So this example is an example of complex which is called as inner orbital complex, low spin complex, or spin paired complex which is called. So here now the orbitals which is vacant orbital, that is now it is called as, after intermixing, it is called as hybrid orbital, that is d2sp3 hybrid orbital. These orbitals, how much are in number when you count it? 1 2 3 4 5 6. Now the 6th orbital, how it is 6? 2 orbital of d, 1 orbital of s, and 3 orbital of p, that is undergoing intermixing. So as we have learnt in the hybridization, how much number of orbitals undergoing hybridization, that much number of hybrid orbitals are formed. So that means 6 hybrid orbitals are formed. These 6 hybrid orbitals is actually the 6 pair of electrons from the 6 ammonia molecule, that the ammonia molecules are contributing the electron to the hybrid orbitals of central metal ion and forming a coordinate covalent bond. Because here the central metal ion is not contributing the electron to forming the bond, only the ligands are contributing, because ligands are acting as a Lewis base that will contribute the electron to the central metal ion, which act as a Lewis acid. So this is acting as a Lewis acid, central metal ion, and the ligands are acting as a Lewis base. So this type of bonding is called as coordinate bond, as we have already discussed. So here only one is contributing the electron. So which one is contributing? Ligands, that is ammonia. So what will be the geometry for this? When the hybridization is d2sp3, the geometry is octahedral. The geometry of it is octahedral. And from this concept, we can identify the magnetic behavior, whether it is paramagnetic or diamagnetic. When you look at here, the all electrons are paired here. That is, in this case, all electrons are paired. Therefore, it is having diamagnetism. It shows diamagnetism, diamagnetic behavior. It is colorless. So this concept is as it is. That is, if there is a unpaired electron, then it is colored and paramagnetic. If all electrons are paired, then it is diamagnetic and colorless. So this is actually colorless and diamagnetic. Next example we are taking here, that is COF6 3 negative. This complex here the ligand is actually F, that is F negative is the ligand. This is actually a weak field ligand. It is weak field ligand. So which does not causes the pairing, as the strong field ligand causes the pairing of electron, but weak field ligand F negative is a weak field ligand, it does not causes the pairing. So here when you look at the central metal ion, that is having the central metal ion having the oxidation state CO3 plus. So when you write the configuration for CO3 plus, there is 6 electrons in the 3D, as we have done for the previous example. In that also CO3 plus, that is 3D6. So we'll be making the 6 electron in this way. 4s, 4p, 4d are empty. Here again the coordination number 6. So the possibility, what are the two possibility of the coordination number 6? How we find out coordination number? Because F is 6 in number. So coordination number 6. So the two possibilities are either D2sp3 or sp3d2. So from this, any possibilities are there? When there is a weak field ligand like fluorine, so more possibility is sp3 D2. This is what I am giving the hint to you. Without doing the hybridization, if you want, you can predict the hybridization by using this concept, that is coordination number 6. So the two possibilities are D2sp3 or sp3d2. But if the weak field are there, then the more possibility is sp3d2. Now let us see how it is possible here. As here it is a weak field, so it does not cause us a pairing. So the d electron, it remain as it is. It does not undergo pairing, but it require 6 vacant orbitals are required, because here 6 fluorines are the ligands which is getting binding. So 6 vacant spaces are required. In order to form coordinate covalent bond, 6 vacant spaces are required. Now which orbitals are involving in the hybridization here? That is 4s orbital, and there are 3 4p orbitals. So total 6 orbitals are required, and here 2 4d orbitals are involving in the hybridization. That means the orbitals which is undergoing mixing are these orbitals, that is 1s, 3p and 2d orbitals undergoing intermixing. So what will be the hybridization? As here p3 and this one is d2. So what is the hybridization now? It is as p3d2. Now look at here, the outer d orbitals are involving in the hybridization, therefore it is sp3d2. The previous example, in that inner d orbital, that is n-1 d orbitals were involving in the hybridization, therefore there we are using d2sp3. Here outer d is involved, therefore it is sp3d2. That is d2 is written after sp3. It shows that here this d is actually nd orbital. It is nd orbital. So this hybridization is sp3d2 hybridization. So here 6 hybrid orbitals are formed, that is sp3d2. These are the 6 hybrid orbitals. So these 6 hybrid orbitals, the 6f, that is the ligand 6f negative, it will contribute the electron. So contribute the electron and form the coordinate covalent bond with the 6 hybrid orbital of central metal ion. It forms a coordinate covalent bond with the central metal ion. So what will be the geometry for this? Because when the hybridization is sp3d2, as we have learnt in the table here, when the hybridization is sp3d2 where the coordination number is 6, what is the geometry? Octahedral. So the geometry for this one is octahedral. What about the magnetic behavior? When you look at here, there are some unpaired electrons available here. How many number of unpaired electrons are there? That is 1, 2, 3, 4. 4 unpaired electrons are there. So that means this is showing paramagnetic behavior and it is colored. Why it is colored? Because of the presence of unpaired electron, it is colored. So when you want to find it out the magnetic moment, you have to use the same formula which we have learned in the D block chapter, that is spin only formula will be using, and we will be finding out the magnetic moment where n is equal to number of unpaired electron. Here it is 4. So you have to use that formula. If you remember what is that formula, that is u is equal to under root n into n plus 2. This formula you have to use where n is equal to 4. So 4 into 4 plus 2. So when you solve this one, it will be something 4 point something. So this is what actually when a hybridization is explained, that is it is explained in the magnetic behavior, and the magnetic moment we can find it out in this way. Let us do one more example, that is NiCl4 2 negative. Here the central metal ion is nickel ion. So what is the oxidation state of nickel in this? That you have to find it out by using the X method, that is Ni2 plus. Oxidation state here, it is 2 plus. As we know that the ground state electronic configuration for nickel, because its atomic number is 28, is 3d8 4s2. So that is for the nickel. But for Ni2 plus, what is the configuration? That is 2 electron you have to remove from 4s. That is now it is having 3d8. So 3d8. So 8 electrons is made here, that you can show here. See here, 8 electrons are available in 3d. That is 3d8 of nickel 2 positive. So in this example, it is directly written 3d8. Better you can start with nickel. First you make the orbitals for nickel. Then you remove the 2 electron from 4s. Then you will be getting for nickel 2 plus ion. Now here the 4 ligands are there, that is chloro. Cl is a weak field ligand. According to ligand field theory, it is a weak field. So it does not causes a pairing. So when it does not causes a pairing here, so the d orbital electron will remain as it is. So here 4 is the coordination number. 4 is the coordination number. So how much vacant orbitals are required? 4 vacant orbitals are required. Here, depending upon the number of ligand, the vacant orbitals are required for bonding. Here 4 Cl are there. That means how much vacant orbitals are required? 4 vacant orbitals are required. So that is actually here the orbitals, 1s orbital and the 3p orbitals undergoes intermixing. Then only it become 4. 1, 2, 3, 4. 4 are required because here Cl is 4. So these orbitals undergoes hybridization. That is 1s orbital, that is a 4s orbital, and the 3p orbitals undergoes intermixing. So it results in the formation of which hybridization? sp3 hybrid. It is an sp3 hybridization and form sp3 hybrid orbitals. Now these orbitals are called as sp3 hybrid orbitals. Why? 1s orbital and 3p orbitals are undergoing intermixing. Therefore it is called as sp3 hybrid orbitals. And that orbitals are called as sp3 hybrid orbitals. Now when the sp3 hybridization is taking place, what will be the geometry? That is, the geometry is tetrahedral geometry. So from the sp3 hybrid orbitals, the 4 Cl negative will actually contribute the electron for sharing. So here the coordinate covalent bond, that is 4 coordinate covalent bond is found between the 4 chlorine with the 4 hybrid orbital of central metal ion. So thus it forms a tetrahedral geometry, that is M is representing the central metal ion. Here it is Ni. What is M here? It is Ni, and the ligands are taking the 4 corners of a tetrahedral geometry. Now here it is necessary to keep the charge what it is given in the complex. So when you are making the geometry for this complex, what you need to write? You need to keep the charge properly. So in this case, Ni is the central metal ion, that we have to write Ni, and we have to make the tetrahedral. So 4 Cl, so that Cl will occupy in that position, and overall charge you have to keep it, that is 2 negative. So that is important to keep the charge on it, that is 2 negative charge. So this is how we used to make the geometry for a complex. But here it is only that a geometry is shown. You have to make the correct symbol for M, L, depending upon the example what it is given to us and keep the correct charge here. The charge what is given on the complex sphere, that you have to keep the overall charge on that here. So this is what the geometry. What about the magnetic behavior? Here there are unpaired electrons are there. Therefore, they are paramagnetic and colored. So this is what some of the examples which we have discussed. Some more examples will be going to discuss in the next video session. So this is all about this video. Have a nice day.